we've spoken previously about how the position of our particle can be expressed in terms of two parameters. And so our typical calculus rules apply to that position vector. So if our position can be expressed as some function of t, well then our velocity and our acceleration can also be expressed as a function of t, simply by differentiating and then obviously integrating if we want to make our way back through acceleration, velocity, etc. So all the same things apply. Again, we'll introduce initial conditions and all those sorts of things to help us find integration constants. So if we have a bit of a look there, obviously we can sort of see that the velocity vector is the antiderivative of the acceleration one, which is just the integration of the individual components. All right. Okay, so r double dot of t, or the acceleration, is given by some 10I minus 12k. Find the velocity if we've got an initial condition there. So again, we've just got our antiderivative, integrate with respect to t, so we introduce the t variable. T equal to 0 gives us our c constant. And so then typically what we would do, we'd group the I components together, any j components and any k components together. All right. And then once we've got that, we're then in a position to get the position vector. Again, we have an initial condition given, so we integrate again. So 10t, 10 to the 2 on 2, etc., etc. Again, we've got our d constant, put t equal to 0. And again, they're all got elements of t in there. So d is just equal to 2k. And so we introduce that 2k into our k component of the position vector. All right, so it's the same rules as previously. Okay, same sort of thing. R double dot of t is equal to negative 9.8j, so our particle might be falling. The only acceleration is in the vertical component. So again, R dot negative 9.8 tj, substitute in t equal to 0, there's your c component. Again, just make sure that you group the right terms together. So the j components are 40 and negative 9.8 t. Integrate once again, we get our 30 ti, 40. I left the t off there, haven't I? Oops. Undo. Let's get that t in there. 30 ti, 40 t minus 4.9 t squared again. T equal to 0. We just get d equal to whatever it was, 0, because they're starting from the origin. And so we get our position. All right. Speed, don't forget, is the magnitude of your velocity, distance traveled, where you start, where you finish, and the magnitude of that. All right, so here's another example here. So curve defined in terms of cos and sine. R dot, we're just going to differentiate, aren't we? dr dt. So position dx dt is velocity. So derivative of cos is minus sine. So let's just make sure we got them right. So negative 2 sine t, derivative of sine is positive cos. That looks okay. Double dot, derivative of the velocity vector. Derivative of negative sine will be negative cos. Derivative of positive cos will be negative sine. Find the gradient of the curve at the point xy where x equals, okay, so the gradient is dy dx, isn't it? Yeah, which can be from a chain rule, dy dt dt dx. So there's my x, there's my y. So if we work out those, dy dt times dt on dx, we get a negative 3 on 2 cot t. All right, off we go.